In this video, we're going to talk about a cosmetic change that makes things easier once you know how to use them. I say easier because in acids and bases equilibria, you usually have a very large or very small numbers, and the idea of manipulating those very small numbers is sometimes not convenient. So what we do is to work in the logarithmic scale. In other words, we will take logarithms of concentrations and constants so that instead of working with exponents 10 to the negative 14 or 10 to the negative 10, we're gonna just take the logarithm of that and the numbers become more reasonable. So we're going to define the pH as the negative log of the concentration of hydronium ion. So for example, if your concentration of H3O plus is an ugly number as 10 to the negative 7 molar, if you take the minus log, it means that the pH of this is 7. If this were positive, it would be negative 7. So, but because it's negative, the pH is plus 7. So pH 7 is typical of a neutral solution. Okay, we will do the same for pOH. So if the concentration of OH negative in a different solution, let's say that it's an acidic solution, is 10 to the negative 10 molar, the pOH is 10. Okay, you just do, not that you, in this case, if this were like 5 times 10 to the negative 10, it would not be 10. You would need to put this into the, I believe it would be around, let me see, probably it would be around 9.3 or something like that. You would need to put this into a calculator and do the log and 10 base. Okay, and of course we can then use the relationship that we knew as the autoionization of water, because if you take the log of this equation, it means that pOH and pH have always need to be 14. Okay, so this means that when the pH is 7, the pOH has to be 7. If the pOH in this case is 9.3, the pH, so that when you add them up, is 14, they have to be 4.7. Okay, so notice that these numbers are more convenient because then we can talk about, like, vinegar has this pH around 2.4, your stomach actually has a pH around 1, etc., etc. Okay, so notice that we will add a p in front of the magnitude when we do the negative log. So the same will be for a constant. We will talk about the pKa when we do the negative log of Ka, and pKb when we do the negative log of Kb. And knowing that relationship, if you remember, Ka times Kb is equal to 10 to the negative 14. This means that pKa plus pKb is equal to 14. Just properties of logarithms. Okay. Again, this is a cosmetic change. Nothing really is new. We're just trying to eliminate all those very tiny numbers and work in the logarithmic scale. Okay, so let's see if we can. Oh, by the way, this slide is just to show you how the ugly numbers translate into integers. They're not integers, of course, because if this were to be 5, then this would not be 0.00. But there are definitely numbers between -5 and 10 or 15, so therefore they're easier to deal with. Okay, so let's see if we can solve problems just with the additional layer that now we're going to talk about pH and pOH and pK instead of their corresponding very tiny numbers. So it's saying that you have a solution of pH 3.5, and it's asking for the concentration of OH negative and H3O plus. So if pH, which is the negative log of H3O plus, is 3.5, how do you get the concentration of H3O plus inside the log? Well, you do the 10 to negative 3.5 molar. There you go. You got the concentration of hydronium ion. There's two ways to calculate the concentration of hydroxide. You could say, well, I know that pH and POH is always 14. This means that POH, it'll be 14 minus 3.5. So that's 10.5. So concentration of OH negative is 10 to the negative 10.5 molar. Okay. The other way would have been using already this, the concentration of OH negative. So skipping the logarithmic scale and 10 to the negative 3.5. This will give you the same result. Okay. So a little bit more intricate. In this case, is asking for the pKa if you have a 1 molar solution of an unknown acid and the pH is, again, 3.5. How can I know the concentration? How can I know the equilibrium constant? Well, I know that any acid dissociates in water, behaving like an acid. And so I know initially I have 1 molar, okay, and I know that this is 10 to the negative 7, but it's pretty much 0, so I'm not going to think too much about it. There's going to be a certain amount of X disappearing from the acid and appearing in the products. All right, so this means in equilibrium, 1 minus X, this is X, and this is X, and my Ka is X squared 1 minus X. Well, the thing is, I know already how much X is because the pH is 3.5. This means X is this, and this is 10 to the negative pH, 10 to the negative 3.5. This means my Ka is 10 to the negative 3.5 square, 1 minus 10 to the negative 3.5, which is going to be pretty much around 1, so we could just do that. That means my Ka will be, if I approximate the denominator as 1, this will be 10 to the negative, this 2 times this, it's going to be negative 7. Okay, that means that my pKa is the negative log of Ka, that is 7. There you go. We got the pKa of the solution. Okay, notice there's nothing new, just that you have to be able to go from pKa to Ka back and forth, and from pH to concentration of, so from this one to pH back and forth. That's important that you can do both. Okay.